And then we'll do that 13.7 number 2 question. And then we'll go back. And the exam is basically on 6 sections, 13.2 to 13.7.
Not one.
13.1 is just double integrals over rectangles. That will not be on the test.
Okay.
Doubling over a rectangle. So you
Are you sure?
So we'll start at 13.2 for your review. Where we do double integrals over regions that are a little more complicated than rectangles.
Just give us again.
Rectangles? There's going to be some rectangles in 13.7. Rectangles in the UV plane. Right?
These are actually
Okay, yeah, so let's go ahead and do this one. So here, we're going to do a change of variables to evaluate this integral. And we have to do a transformation here. This one is from 3-dimensional space to 3-dimensional space. And we need to do a 3-dimensional Jacobian then. And we will come up with our transformation here. They make it pretty straightforward in terms of, we see that there's a y minus 2x, a y minus 2x. So that's probably the candidate that works best for you, that u equal y minus 2x. And then u would go from 0 to 1. And the way the book always writes it is 0 less than or equal to u less than or equal to 1. And then if we look at the next pair we have z minus 3y and z minus 3y. So that's going to give us a choice for v. And it looks like that variable v will then go from 0 to 1.
Yeah, so where are you getting the u and v from?
From those equations. So from those equations, I see that they have they have this similarity. We have y minus 2x and y minus 2x, so those are parallel lines. And so that's your candidate for you. Let you represent the variable part of the parallel lines. And then the constant part will be indicated by the right-hand side of the equal sign. Similarly, here we'll let v be the variable part of these parallel lines, or maybe I should say parallel planes because we're in 3 space. And then z minus 4x for the last one. So we're looking at those equations and noticing that we have this parallelness going on. And then we can let u, v, and w represent the variable parts. Okay, so now we can't find our Jacobian until we solve that system for x, y, and z. The Jacobian is always the partials of x with respect to u and v, or in this case, u, v, and w. So we need to solve this system here and write our x, y, and z as dependent variables. So we have to solve for x, y, and z. So usually back in college algebra, you learned that if you have a 3-variable system, one way to do it is to eliminate the same variable twice. So eliminate x from 2 equations, eliminate it from 2 other equations, and then combine those two. So that's one possibility. Notice here that this first equation is missing z, right? So we could use this equation and then eliminate z from the other 2, and that would be one way to pare it down to a 2-variable situation. So let's do that. We're going to take equation 2 and 3, and if we subtract them, v minus w will be minus 3y plus 4x. So that equation now has x's and y's. This equation has x's and y's. So let's combine those two. So let's multiply the top equation by 2. If we multiply the top equation by 2, so that equation is coming down right here. And I doubled it so that when I add those together, then x is gone, and the only letter left in the only x, y, z left is y. So then we've solved for y in terms of x, y, and z, in terms of u, v, and w. So add those together, x's go away, and we end up with minus y on the left. And on the right, when we add, let's put it in order. We get 2u plus v minus w is equal to minus y. So let's come over here and write our stuff out. So y is equal to negative 2u minus v plus w. So we've got one of them done. Now if we plug that equation into this one, we could get z, or if we plug it into this one, we can get x. All right, we just substitute it in. Let's go ahead and substitute it into the first one and get x first. So we know that u is equal to, so this is equation 1, and we're just replacing the y with what we just found in terms of UVW, and then minus 2x. So we should be able to solve that one for x now. So we're going to move everything over. We have 3u plus v minus w is equal to minus 2x. And then solve that for x. We'll put it over there with our y equation. Put it right up there. Solve for x. And x is going to be negative 3 halves u. Negative 3 halves u minus 1 half v plus 1 half w. And then we just have one to go. We have to solve and figure out the equation for z in terms of u, v, and w. A couple of ways we could do it. We could plug this right back into there. That would work. We solve this one for x. We could plug the x into that one and solve for z. Doesn't really matter. Whatever you want to do. Does not matter which way we go. So let's take the third equation here. We have w equals z minus 4x. So let's just multiply x by 4. So I'm going to multiply that one by 4. And that will allow us to get to z. So distribute the 4. And isolate z. Isolating z will give us how many u's? Looks like negative 6u. How many v's? Looks like negative 2v. How many w's? Add that over, so 3w. So there it is. So that's our system with x, y, and z as the dependent variables, and now we can find the Jacobian factor. Yeah?
Yeah, are those the only x, y's, and z's you can get from your initial...
Yep.
Okay, because I got x equals v minus w, z equals 4v, and...
Yeah, no, well, as long as if you use these substitutions, those are the only x, y's, and z's to get. If you use these substitutions. If you chose different expressions for u, v, and w, you could end up with different equations.
I'm pretty sure I chose the same expression.
Yeah, those are the ones you should get. I can look at it during the break. Yeah.
So does it matter which ones you choose? So could I do like w is z minus 3y instead
Yeah,
of v?
and that does not matter.
Okay.
That won't matter. You'll just have your range of these ranges will just be different, right? If you put this one up here,
Right.
your v would be 0 to 3 instead of 0 to 1.
That's not fun to grade, huh?
No. No. But what grading is ever fun? Right? That sounds like an oxymoron. Okay, so then our determinant is going to be our Jacobian. So we have to take the determinant of a 3 by 3. And how many have never taken a determinant of a 3 by 3? Right, exactly. You've all done it.
It's cross product.
Cross product.
I don't
Nice.
remember it.
I'll show you it again.
Perfect.
So the interesting thing about a 3 by 3 is that you have a zillion choices. With a 2 by 2, you have no choices. It's very determined. So if you have this A, B, C, D, the determinant is AD minus BC. It's the main diagonal product minus the other one. So with a 3 by 3, you have a lot of choices. You can choose to expand, if you will, about any row or any column. It does not matter which row or column you expand about. The 3 by 3s that you have done have been about the top row where you had I, J, K. right? And that's the most straightforward way to do it. We will see another determinant in a couple minutes where there's some zeros that it might make sense to expand about a different row or column. Now, when you're doing this expansion on a 3x3, there is an embedded sign array. So in the top row, this is the sign array that's embedded. And we've seen that with the cross product, where we have the ijk. Right? We have to switch the sign of the j. Now, if you wanted to expand about a different row or column, you can, but you just have to extend this sign array, has to keep on going and cover every row, every entry of every row. So if you expanded about the first column, it would be -3/2 times the determinant down here. It would be minus a minus would be +2 times the determinant of those 4 entries. And then it would be -6 times that
Are
one.
we sure we've done this before with 3
Whoa.
You've done it with a 3x3 with a cross product where you expanded about the top row. So
But the top
that's,
row is just ijk.
yes,
So you
exactly.
just multiply by ijk.
Yes,
Oh.
yes. Yeah,
So we
So
do
technically,
the two
pretty
last
much
row with do the same with the
Equal.
cross product and use that for the top row and the result, our result, right?
yeah, so there are 6 choices here. You can expand about this, or this, that, or that. And it does not matter. They will all give you the same determinant. The one you're most familiar with is top row, so let's just stick with that.
Okay.
Let's not get fancy. We're going to expand about that row. That makes it the most simple because it's the most familiar to you. So this is going to be -3/2. Let's just write it out in gory detail this time. And I'm going to get rid of all these guys just because I think that will cause confusion if you look at it later. So for us, we're expanding about that row, so we put the plus, minus, plus. It's going to be -3/2 times the determinant of this. They call this a minor, so it's the determinant of that minor matrix, where you cross out the row and the column that this -3/2 came from. So you cross out those two, you get that minor matrix.
Not so bad.
Hold on.
It's not so good.
Only
When you said gory detail, I didn't know you meant that.
And so then +1/2, we use the sign array value there, we change the j, and then the middle column is crossed out, the top row is crossed out, these 4 guys are left, so those 4 entries we put in here, we take the determinant of those 4. In practice, you would never write this down. You would just cross that out, and you say -6 minus -6. You don't have to write this step, but I'll do
Oh,
it.
trust me, I will.
Yeah, if you feel, there is no harm in doing it. So then our determinant, here we get -3/2 times -3 plus 2. -3 plus 2 is -1. Go to the middle. We've already changed the sign. That's how it got to be +1/2. And then it's -6 plus 6, 0. And then +1/2. This is +4 minus 6. +4 minus 6 is -2. Let's go down below, I guess. So then our Jacobian value is 3/2 minus 1, so it's +1/2.
Nice.
So try what I said you could do. Try to expand about a different row or column, during the break or later, just to make sure that you see that you can. There's 6 choices. It doesn't matter. Yeah.
Is that minus the sign mabobber?
Sign array.
Sign array.
Mhm.
So it changed that 1/2 to a positive.
Yep.
And that's why. Okay.
That's exactly right. So here, so that right there is a combination of minus the sign array value and the entry value.
But the
You
positive
multiply those two.
doesn't affect the negative, so it's just like a regular being
It's like
multiplied by
-1 times -1/2. Right. Yep.
And so that's only going to affect where you're expanding about, not like when we were doing the cross products where it was, I guess these are like mini cross products, like that you're going to multiply by those numbers you're expanding.
Yeah, so these guys right here, when we were doing cross product, we said, okay, this is the I, and we multiplied by that determinant.
Yeah,
And then this was J, and we did this determinant and changed the sign.
but we only have 2 rows, right?
Well, we have 3 rows. The top row is IJK.
Or sorry, I mean, Because there would be one vector and then there'd be another vector. But we never did 3 vectors.
Are these vectors?
Well, I'm thinking, because that's what I'm thinking with cross
You
products.
can think of it as vectors. If you did this, if you want to think of these as vectors, does anyone know what the value of that 1/2 is? This is called a triple scalar product. And each one of those vectors, if you imagine them aligned at the origin, this finds the volume of the corresponding parallelepiped.
Oh.
Yeah.
Thinking of the vectors.
You know, just like a determinant will find the area of the corresponding parallelogram, a triple scalar product, which is what this represents, the determinant of a 3x3, if you think of each of those as vectors emanating from the origin, then there's this weird parallelepiped formed. This finds the volume of that parallelepiped.
Ruby.
Yeah. Okay, so practice and see, make sure that if you did the middle column, you'd have a minus there, a plus there, and a minus there, that you get the same number. You do it a couple of times, you're like, oh yeah, I get it, but I'll just go around the top row because it's easiest. So now let's find our volume. Or, yeah, this was volume.
Does
Question?
it make sense to cross out a certain row because it would be easier?
Yes. If there are zeros, like if you have one row that's got a couple of zeros, that's the fastest row because then these multipliers that you get in front, if a couple of them are zeros, then it's a lot quicker. Yeah. Okay, so what is our volume then? So our volume is the triple integral of, we can go 1/2 times du dv dw. And those were all constant limits of integration now. You went from 0 to 1. So 0, 1, 0, 1, 0, 3, 0, 1, 0, 1, 0, 3. And we're done. We get 3/2. So that's our volume.
We're done. 3.
Does everyone see why we're done?
Yes.
There's no U, there's no V, there's no W, so we multiply by 1, multiply by 1, multiply by 3. Right? Right? There's no U, no V, no W in the integrand, so we just multiply by the length of each interval. Okay, so that is the volume formed by these 6 planes, right? There's 6 planes there that are forming a solid parallelepiped type thing floating around in space. All right, let's try one more of them. So again, find the volume where D is bounded by the upper ellipsoid, the upper half of the ellipsoid, and the xy plane, and they tell us. Now this is so kind of them.
This is so.
So kind. They tell us what these should be. And you are going to tell me what they're going to be if I modify that ellipsoid slightly. You are going to tell me what the transformation should be in 2 minutes.
So what are we gonna have to do in turn of their such kindness? Because they're so kind.
They're so kind, which makes me feel like I should be kind too, right?
Oh,
Yes.
wow.
Right. But I will extend what they've done so that you can see why they chose those subs. You can probably start to see it already, but we'll look at it 1 second. So first, finding the Jacobian here is a total breeze, right? What do you think the Jacobian of this matrix is going to be?
6.
No.
2.
No.
2.
I heard it, I think. 6. Who said 6? Couple of sixes.
We've been hearing 6s ever since you asked.
Oh, really?
Yeah, there's been a lot of 6s.
I can't hear that.
Yeah, Haley
first
said
one.
6 and you were like, no.
Not that 6, it's the other 6. The other 6. Okay, so let's see why that is.
Okay.
So let's see why that is. If we throw a sine array, let's do this one about a different row or column just for grins. Let's suppose we know that's a minus, we know that's a plus, we know that's a minus. So what we would have then would be minus 0, which is just 0, right there, multiplied by the determinant of the corresponding minor matrix. So we take whatever's left after we cross out the row and column that that 0 comes from. Obviously that's going to be 0 and you would never write it down in practice, but illustrate the point. Now we go to plus 2. cross out the row and column it comes from, and we're left with the 3, 0, 0, 1. All right, and then we go to the bottom 0, minus 0 is still just 0. Cross out the row and column that it comes from, and we're left with 3, 0, 0, 0. And obviously, these guys are all gone because the coefficient out in front is 0. If the coefficient out in front is 0, you get 0. And then the determinant of this matrix is 3 minus 0. So we end up with 2 times 3, so we get a determinant of 6. And what you're going to see as you do more determinants, if you have a matrix, a 3 by 3, if you have a lower triangular part that's all zeros or an upper triangular part that's all zeros, the determinant is just the product of the main diagonal. That's what you'll see. So if you have 3 zeros here, you're going to end up with that as the determinant. You'll see in practice as you do more of these later in other classes. Okay, so let's take a look then at this transformation. So the volume then is the triple integral d6 times du, dv, dw, and we have to figure out what the limits are. Okay, so that's over the region in the solid object in the UVW system. So let's figure out what that happens to be. So this is whatever that solid object is. What letter are we using for solid objects? I can't even remember. He uses R and S, but I guess we haven't done a solid in space. Let's call it G, whatever it is. It doesn't really matter.
Isn't it just D up there?
D, so D is in the XYZ plane.
G
So-
is in the D.
I don't like G. I'm not doing G.
Okay, do D star. Do D star.
Anything but G.
Or do DS. The Death Star. The Death Star will work because look what happens. When we let X equal 3U, what are we going to get over here when we use our substitutions? When we plug in a 2V, what?
Gonna cancel out.
2b to the y.
What?
Nice
Nice. Trying to
We're
psych
just
you
gonna
out.
get U, V, and W equal 1. Squared.
So what is this thing then?
It's a sphere.
Sphere of radius.
1.
Sphere of radius 1. We end up with a Death Star
Of radius 1.
of radius 1. Death Star of radius 1. And so this integral over here represents 6 times the volume of the Death Star. Times the volume of that sphere of radius 1. Except we're just dealing with the upper half, remember? Because we started with an upper half of an ellipsoid, so we're really just looking for the volume of the upper half of that. So what is the volume of a sphere of radius 1? 4/3 pi r cubed is the sphere, volume of the sphere. So the volume of a half sphere will be 2/3 pi. So this all becomes 4 pi. 6 times that. Yeah, 4 pi. So,
Do we have to know that?
volume of sphere? Highly recommended. The volume of the sphere, 4/3 pi r cubed.
On it.
Definitely.
On it.
Yeah, I'm on it. Now, what about, so first off, let's analyze the substitution. Everybody sees why we chose what we chose for our transformation equations? So if this was x squared over 16, what would you pick for x?
4U.
4u. Y squared over 25, you would pick y equals 5v. So those substitutions turn the solid object into a perfect sphere. I guess all spheres are perfect.
Yeah.
Turns it into a sphere, so that would work. Now, one quick question. We've talked about the area of an ellipse. So if we have this ellipse right here, where this dimension is 2 and this dimension is 5, the area of this ellipse is 2 times 5 times pi. Is the same true for an ellipsoid? No, that's an ellipse. But can we extend that idea? When we look at the sphere equation, it's 4/3 pi r cubed. So would the volume of an ellipsoid be 4/3 pi times whatever letters we want to use? Let's find out. So what would the letters be then?
UVW?
So what would the, so we would have a 3, a 2, and a 1 as the semi-axis lengths, half the axis length. What did I say, 3, 2, 1?
That'd be 6.
So we get 24 over 3 pi, which is 8 pi. That's the full ellipsoid. This is half the ellipsoid. So divide that by 2, and that would give us the volume of our ellipsoid.
You bypass the integral just completely.
Yeah.
Nice.
So we can bypass the integral completely if we know our geometry well.
Let me
Andrew?
just say this out loud to make sure I got it right. We
Yeah.
set up the integral for the volume of the whole sphere, but then we only needed the top half of it because it was the top half of the ellipsoid, right?
Yes.
'Cause it says
So because this solid that we're looking at is the top half of the ellipsoid, when we transfer it over here, it's corresponding to the top half of the sphere in the UVW system. Yeah.
Does that mean it takes care of that for us, like within the?
Right. Within within this transformation here, that transformation is going to, it's going to create a full sphere, but the upper half of this ellipsoid is going to correspond to the upper half of that sphere.
Okay, so we don't need to divide by 2 if we did it just the way you did here.
Mhm.
But if we integrate through, or do we need to divide by 2 or?
Well, you would, what sphere, what coordinate system would you want to use over here if you were trying to find the volume of a sphere?
Spherical.
You would use, excellent. If you want to find the volume of a sphere and you don't know 4/3 pi r cubed, you would use spherical, and spherical, your rho would go from 0 to 1 in this case. What would phi go from for a sphere? Or for a hemisphere, I should say. If we were doing the whole sphere, it would go 0 to pi, but if we were doing just that hemisphere, it would go 0 to pi over 2. And then theta would go 0 to 2 pi. Yeah?
Can you remind me again why you only go to pi on the sphere?
Yes.
For phi instead of 2 pi?
And so the range on phi is 0 to pi because you can catch every single point in three-dimensional space by letting rho be unlimited, 0 to infinity, theta going 0 to 2 pi, and phi going 0 to pi. If we went 0 to 2 pi for phi, we'd have double ways to describe points. So for example, if we're trying to get, if you imagine the latitude, if you imagine the Earth with latitude lines, those latitude circles around, phi takes you down to a latitude circle, and then theta takes you around to the backside. Right?
Right.
So if your phi is right there, then theta can get you all the way around. If phi is down there, theta can get you all the way around. So you can uniquely represent each point by just going 0 to pi for phi.
Okay, thank you.
Make sense? Okay. All right, so let's go to this one. This was the, is this the trough one?
Yeah.
No.
Yeah,
Isn't this
or
number
no,
2?
it's 97.
I don't even know what this is.
No?
Okay,
No,
find
wait,
the,
what is this?
find the volume of the column with square base and cut by this plane.
Do you know what one this is?
No.
No, it's probably the second.
Is this 13.7?
This is 13.2.
Oh, this is 13.2 and this one is 13.7?
Yes, that one. Let's do that one.
Okay, let's do the 13.7 one first. Let's finish off 13.7 and then we'll go to the other one. Oh, right. I guess there's a clue that that's not 13.7 right there. There. Now I see the 13. Okay. Now it's making sense. Okay, sketch the original region in R, the R plane. Blah, blah, blah. Okay, so blah, blah, blah. When we look at this, x goes 0 to 3. Y goes from negative x over 3 to 2 minus x. Okay, so that means that we're thinking about a vertical element because the vertical element has a y function on top, a y value and a y value. So we first are looking x 0 to 3, and then we're going from a negative sloped line over here up to another negative sloped line. Oh, there's only one of those. It has to be this one, just by that very logic. Right, this line has a slope of -1/3. This line has a slope of -1. All these other ones have, at least the lower line is all sloped positively. So it's got to be this one where they chose a vertical element. So now we want to convert over to the UV plane. And they give us the transformations to use here. We're going to look at these 3 points. If we look in the XY plane, we'll take a look at these 3 points. Let's see, that one looks like 0, 2. This one looks like the origin. And that one is, it looks like 3, -1. We probably should double check. If we plug in x equals 3 here, we get -1. If we plug in x equals 3 there, we get -1. So it's going to be 3, -1. And then we use our transformations over here to figure out what the u's and v's are. Now the transformation equations are written with x and y as the dependent variables, so we'll have to convert that so that we have u and v, so we can plug in x's and y's. So this is pretty simple because if we solve for u is 1/3 x. And then to get v is going to be y plus u. And why did I do that? What am I trying to solve? I'm trying to solve for v.
And u is equal to 1.
Oh, and then u is equal to 1/3 x. Thank you. I was like, wait, why did I do that? Now I know why I did that. Okay. Now I know. Because we want to solve for v, right? So we want to substitute the x from above. All right, so let's plug in. If x is 0, then u is 0. And then down here to get the v value, x is 0, so we get 2. Down here, plug in zeros, we get zeros. Here, plug in 3 up there, so we get a 1. And then we get a 1 minus 1, which is 0. So in the UV plane, we have 0, 2, 0, 0, and 1, 0. So we get this triangle in the UV plane. It'll be our secondary domain. That triangle is going to be easier to integrate over than the first triangle. I mean, not a ton, but maybe with this, that thing looks pretty hideous to integrate over that triangle. Will?
Yeah, what's the y coordinate of that second point? 2.
The y coordinate here?
Yeah, it looks like P.
What's 0?
0. 0, 0.
Oh, that's 0.
That's all right. I'll rewrite it.
Thanks.
0, p. No. 0, 0. 0, 0. Pair of zeros. Okay, so now let's use our transformations to rewrite. Well, let's find our Jacobian first. So Jacobian, that's going to come from this pair of equations where x and y are the dependent variables. So we have to take the partial of x and the partial of y with respect to u's and v's. So it looks like we're going to have 3, 0. Let me know if anyone's not sure about how we get these numbers. So our Jacobian is 3. That means our integral. We have x squared. We said that we're going to let x be 3u, so that's going to be 9u squared. And then we have to replace that square root with what it's equal to in terms of u and v. So we're going to have x plus 3y. So x plus 3y. 3y is 3v minus 3u, so the u's cancel and we just get 3v in there. And then the Jacobian,
Times 3.
which we could put out front. That's totally fine. And then du dv, because it makes probably the most sense to use a vertical element here. So u is going to come 0. Oh, so I guess I should do.
Found it.
I did one. Did I do the right order? Du dv.
No.
If I use a vertical element.
No.
Yeah, if I use a vertical element, it should be
dv
dv du. Should be dv du if we use a vertical element. dv du. So the u's are on the outside going 0 to 1. The v's are on the inside going from 0 up to that line. That line has a slope of -2 and a v-intercept of 2. So -2u
Oh,
plus 2.
Positive.
Positive 2, positive intercept. And then that's pretty easy to integrate.
It's not.
Is it?
It's
I don't
not.
think it is.
It's not.
This is hard.
Oh, this is hard now?
Look at
I don't think-
that is
Think
my
you
work,
do it.
and I didn't get
All
it
right,
right.
I'll keep going.
This is the 23rd problem.
Yeah, this is
Okay.
that's the only reason anyone asked you to do this problem, and you were about to skip it.
Oh, is this last part?
Yeah.
Okay, so we get 27 square root of v, square root of 3, 0 to 1. We're integrating root v, so we have v to the half, so v to the 3 halves times 2/3. And that's 0 to negative 2u plus 2 du. Maybe we should have done du first. Pull out the 2/3, what do we get? 18 root 3 in the front. 0 to 1. So then we have u squared. Pardon? Don't have a question? Okay, so we've got that. So everybody okay with that? We could factor out the 2 out of that to just clear out that coefficient if we want. Let's do that. Let's just get rid of that 2 that's in there. Let's clean it up a little bit. So let's factor out a 2. So if we factor out a 2, that 2 has to be raised to the 3 halves power. So that's going to be a 2 root 2 that comes all the way to the front. Whoops. 2 root 2. 2 root 2 all the way to the front. Times 2 root 2. And then this will still be the same. Now this will be minus u plus 1. Did we have to do that? No. Okay, so that substitution, u sub. So let's
Will
let.
you sub?
Or we'll use a bad letter.
X sub.
What sub? Oh, let's do x substitution. We'll go back to x's.
Why the hell
Let's
not?
go back to x's. That's a great idea. I like that idea a lot. Okay, so we go back to x's, and we're going to have to isolate the x to get that u thing there. Or isolate the u, I should say. So it's going to be u equals minus x plus 1. So this will be, this is 36, square root of 6, integral. What are the limits? When we let u be 0, x is going to be 1. When we let u be 1, we're going to go from 1 to 0. And then we square u, so that's going to be x squared minus 2x plus 1.
And then x to the 3
And then
halves.
x to the 3 halves.
Here's the part I messed up.
Wait, after this?
Wait, okay, hold on. Isn't there a negative?
From, yes, there is a negative. Let's put that there. Yeah, because du is negative dx.
Because you're gonna get.
Yeah, and in my mind, I was thinking we'll just switch these two. Right, we can
Oh,
switch.
can you do that too?
Yeah, we could also switch these and make that a positive.
Oh.
Wait, so which one did you do?
He did not
I
switch
did
them.
not do that yet. So we said that du is negative dx, so dx in the negative. In this next step, let's swap them though. Who the heck wants a negative in front and weird limits that go
You already
backwards?
swapped your limits though.
No, we didn't. We didn't swap them.
Those are the limits.
We changed them. We went from u to x. Yeah, so we didn't switch them yet.
So now you're going 0 to 1?
Yeah, so now we're going to switch them and go 0 to 1. And now we have to distribute here, so we have 3 halves plus 2. So what's that, 7 halves? And then minus 2x to the 3 halves plus x to the 3 halves. That's a bad adding. That's 5 halves. So we get that. Do I need to keep going still?
Hold on,
Yes.
hold on.
We might as well finish it. We're this far in.
You guys are killing me!
What are you
That's a
kidding?
5.
I thought you were having fun here.
That's a 5, Will.
Thank you.
Literally. this is
All right, so then we integrate. So we get x to the 9 halves times 2 ninths. We get x to the 7 halves times 2 sevenths. We get x to the 5 halves times 2 fifths. 0 to 1. So then we get 36 root 6, 2 ninths. So we get that. Draw comma line.
Okay, wait.
I'm not adding those
I have a
fractions.
question. So,
You had them.
I know, I got it.
how did you get 7 halves multiplying 3 halves times 2?
I didn't multiply 3 halves times 2. I multiplied x to the 3 halves times x to the 2, which means you add the exponents. 4 over 2
So I did that
plus
for my
3.
other 2 except for that
Four.
one. I just canceled my 2.
Yeah, that you cannot. That would be a mistake. That would be a
Answer
mistake.
is hilarious.
Tell us what the hilarious answer is.
No.
13,824 over 35.
I
I
got
just-
18 square root of 6.
Really?
So is that the number you said, Haley?
Yeah.
I got 64
And does
square
that
root of 6
include the
over
36? Does that include the 36 root 6?
Yeah. Yeah.
Haley,
No, you
wait,
can't have a root.
where's the
Mine
root
is,
6?
I got what Grant got.
yeah, I got
It mixed it in.
64 times the square root of 6 over 35.
Wait, say that again?
64 times the square root of 6 over 35. It's been confirmed by at least one person.
I can
I like
confirm
that.
So where's your
Okay.
third?
We got
So you
three
double
people.
check yours, Haley.
I'm on it.
I
I'm
got
on it.
and that number equals 4.479.
Okay, it was close.
That's what I call it. rocket science.
That's close. So not this thing
There's
then,
no
right?
way it was not close.
It was kind of close.
I got excited.
Slightly.
Yeah.
So I was
Very
just
excited.
missing the root 6 or the root.
It's just
Super excited.
I give up.
Now I know where my mistake was.
Yeah. So
Thank
I
you.
did all that just so you could
So
add 2 plus 3 halves.
Okay, so in the beginning, I think I see my mistake. So in the beginning, you took the root 3 and you just pulled that away from that v. That's what you did.
And the root 3 that we're
And you
talking.
threw it out in front. It's like way at the beginning.
Right.
Way up there.
Yeah, so like up here, you have
Yes.
root 3v, and you just took that out and left the v squared.
Because that takes away the chain roll piece. If you
Yeah.
leave it in there, then you have to do a chain roll piece and divide by.
That's why I lost my square root.
Yeah. That would. Yeah, I think it's easier to just separate this and peel that
12
guy
square root
apart right
6.
there. That's going to be
Why am I
easier.
getting these very nice numbers?
Yes, Mark.
Why did you do u plus 1 as opposed to u squared for your x substitution?
So if we do u squared as our x substitution, it doesn't. It's not gonna give it to us, right? I guess because we can't split this.
Okay.
If we could split that, then I see what you're saying. If we could split that, then we could say u squared. The derivative is 2u, but we can't get to that in there.
Okay.
There might be a way to finagle it, but I don't see an easy way.
We can use integration by parts for it, is right?
If you want, yeah.
Yeah, but it's really not, right?
Well, you'd have to do it. You'd have to do it twice.
Yeah, I did it.
Yeah.
Talking about.
It's like math.
Yeah. If you let now integration by parts is usually UDV. We'd have to use slightly different letters.
X,
Y.
Y.
It's
But
X and Y.
You would let your capital U be this, and your capital DV be that, and then you'd have to do it twice to get that down. It'd be a pain. It'd be a pain. Okay, so that is the end of 13.7. Perfect, time for test. Okay, so let's go to 13.2.
Okay.
13.2, so test is
Do you
13.2 to
know which one
13.7.
this is? Like which number on the homework?
I don't. I would assume that it's near the end, since that's 99.
Yeah.
Do we know which number this was in the homework?
That's not my question.
Does somebody, whose question was this?
I think it was mine. It was the
Oh, is this the trough?
But that's not
That
it.
was like,
But that's not
that's the
it.
last question. I think it's the second to last question.
Oh, so we don't need to do this one?
No.
No, I think I meant 13 too.
Yeah, we did it before.
We already did that one?
Yeah, the last one of particle 2, right?
Okay, yeah, let's not do that one again then. Let's not do that.
Yeah, see, I don't have it. It's number 14.
What number did you say was?
Wasn't that the last one? Number 14 and
Number
13 too?
14.
See if that's it. Yeah, because that would, yeah. This is 14. No, that's 15. 14. No, 14.
That was the one you just.
Oh, it is
Yeah.
14. Okay.
That one.
There it is.
Trough?
Oh, that one. Yep.
Yeah.
Sounds fun
I don't
though.
have to work in that.
It's like you did it before. You did it before.
We did this exact one?
Yeah, we did it before, I remember.
How did I have this much?
I remember doing the trough.
I have it over here. It's not what
Is this not a drop?
It is.
Where did it go?
Or, like, yeah.
Just like
it's a
here.
trough. I call it.
Yeah, this is
Vanished.
totally.
It did.
Send to current page. There it is. We'll just set it up if, So, and Haley, what exactly is your question on it? Was
I just missed the whole like,
the idea of the front, back, top, bottom thing?
yeah, and the cutoff at one of the, at
Okay.
the XY, whatever.
Okay, so this says compute the volume of the solid bounded by the plane. So we're doing a double integral. We didn't know triple integrals yet, but we could use triple integrals, right? We've seen that when we're finding volume, a triple integral of nothing is the same thing as the double integral of upper minus lower or whatever. So you could use a triple, but we'll use double. And so first we have to get a sense of what this object looks like. And the variable part is with z as functions of y. So that's where we really want to focus our attention. These are two planes that are horizontal, z0, z4, simple enough. These two are also just planes, front and back, x equals 0, x equals 7. So the part that's tilted is in the plane that has z and y in it. So let's figure out what that looks like. And that first one, z equals y minus 2, is going to be a line that has a slope of 1 and a y-intercept, or I should say a z-intercept of -2. So -2, and it's got a slope of +1. So it's going to look something like that. We'll get it there. Okay. And then the other one has a slope of -3 and an intercept of -2 also. -3. So that means it's going to go through this point right here, -1, 1. Slope would be -3, down 3/1. Tell me if we need more explanation of anything.
You're just graphing it right now, yeah.
Just graphing it. Just graphing it.
That's where our focus should be, is where we see, constants, but there's a function of something.
Yeah, so the
else.
variable piece is in the YZ plane, right? Because all the other surfaces are planes. That's a plane, that's a plane, that's a plane, that's a plane. And it's true that both of those are planes also. It's just that those are tilted.
They're not on an axle.
Right. So
No,
now let's focus on the z equals 0 and the z equals 4. So these two tilted planes, x is missing, right? So we extrude in the x direction. These two planes are horizontal, so we could project those into the YZ plane because those are horizontal planes. In this essence, they're extruded in the x direction also. So if we think about z equals 0, this would be the z equals 0 plane coming straight out at us. And then the z equals 4 plane would be up here coming straight out at us also. So we should be able to visualize our solid object now. Our solid object is this object right here, that trapezoid, that is pulled in the x direction straight out of the board.
Trapezoidal prism.
A trapezoidal prism. Yes.
Only to 7.
Bad place to spend your weekend.
Oh my god, that's so great.
Okay, so don't avoid at all costs trapezoidal prisms. Now, if you pull this out in the x direction, would we want to use a top-bottom model?
Couldn't you?
Could we? We could, but it'd be hard. Because if we use the top-bottom model, we'd be thinking of a vertical element. Here, that is the bottom, but here, that is the bottom, right? So the top surface is bigger than the bottom surface, so that would be a bad choice just because we'd have to subdivide. You could, but it'd be hard. So that doesn't make the most sense. So we have two other choices. Let's see. Can we use the left-right scenario?
Yes.
Yeah, left-right scenario. This plane would be the left surface, and this plane would be the right surface. We could do that. could we use a vertical element here? I am not a vertical element, but could we use a front-back model?
Yes.
And the answer is yes. We could use a front-back model also. This would be the back surface, which would be x equals 0, and the front surface would be x equals 7. Right, and then we'd use a horizontal element there as well to define
That's
the
what
domain.
they're doing, right?
So it'd be like x equals 7 minus x equals 0. 7 would be in the top.
Yep,
Zero.
yep. So we go 0 to 7. Should we do it that way?
Yeah, I just think
Isn't
my
that the way
confusion
it-
was, I thought that, because I didn't realize it was cut off by z equals 0, I thought there was some discrepancy with all of these, that once they hit the plane that we shouldn't ignore. I just missed that part of the logic, I think,
Okay.
that we shouldn't account for the negative volume, but if that z equals 0.
And now I
wasn't
understand what
there-
you meant, the negative volume. Yes, so
Yeah.
that z equals 0. So, but we still could have a trough with positive volume.
Right,
You know, we could still integrate from here to here.
right, but we would if that z equals 0 wasn't
Yeah,
there.
yeah. Z equals 0, we go down to the vertex.
Okay.
Okay, so if we do a front-back setup, x would be on the inside for a front-back. The back would be x equals 0, the front would be x equals 7. And then we have to do the yz region for the outer two integrals. Again, we'll use a horizontal element there, so z goes 0 up to 4. And then the y's go from that one, that one, this one, that one, over to this one.
You know, the second
Nice,
one
Eric.
is y equals z plus 2. The other one I'm still
And it
solving in my
looks
head
terrible,
of
it sucks.
z plus 2 divided by
Well, it's
negative
not,
3.
but I don't
So
understand
Z plus 2 is the right one.
Why is that there's so?
yes.
And then over here, that one is 3y equals minus z minus 2, so y will equal minus 1/3 z minus 2/3. That's this one.
No, I get the graph.
No, that's the other one.
Why is he sending it
That's this one.
triple? They said it was-
Right? That's that one.
Oh, he's setting up as a triple because he's putting, yeah, why are you setting it up as a
Oh,
triple?
just for fun.
Just for fun? Okay.
So, wait,
On
hold
that
on.
one?
So if we wanted to set this up as a double, wouldn't we just collapse the inner and make that a 7?
Yeah.
Don't you want your,
So is that what that little box out there is?
This little
This one?
box?
Yes.
This little box, what is that little box? The dz if we did dz dx, then we're doing y surfaces. So we're doing that surface minus that surface.
That's our constant.
I don't know what I would put out there. We're not using symmetry of any sort. I would put a 1. That would be my constant, a 1.
But how do you have a triple and they have
yeah, and why
So-
are there surfaces on the middle?
For the 100th time, a triple integral of nothing is volume. A double integral of front minus back, left minus right, or right minus left, or top minus bottom is
Sure.
volume, right? All three of those are all the same. So if you want to write this as a double, then all you do is take away the inner integral, correct?
Yeah, that's 7.
You feel better?
Oh, I see what you did.
No, she doesn't feel better.
Or you could take away the outer integral and drop the 4,
Yep, you could do that also.
which
No,
would
you
lead you to
can't,
dz dx.
because there's
which you want.
these.
Oh, she's right. You cannot do that in this case. You can't take about, you can't, but if we change the order of integration, we could take out the x's instead of the
I think they did it in a different order
Yeah, they did.
than we did, so that's when you get this thing up front, is when you take the top minus the bottom, your functions are on the inside. And then
But we
there's a
can't do
fraction
top
that
minus
comes out.
bottom.
Or not top minus bottom, I mean in the,
Right minus
the,
left.
in the integral, the
Oh, there's a
top bound
constant.
minus the bottom
That's
bound.
Okay,
why they
gotcha.
already solved them for Z. They were trying to be nice to you.
Yeah, they're trying to be.
Yeah.
So if
But
we,
you were like, no, I'm gonna go the hard way.
we can try to do it a different way.
You're missing a third on that.
Up top.
Yeah, nope, bottom one. On the 2.
Oh, 2/3. Thank you. Dividing by 3 here is 2/3. 2/3. Thank you. Yeah. So we have a couple choices there. Just not this choice. Not lower to upper. Front to back, left to right. All right. Next problem. Oh, break. See ya.
Why are the surfaces on the inside for that one? Or are the x surfaces are x equals 0 and x equals
Yep.
7? But then our domain.
So surfaces are always the inner integral, and then the domain for those two surfaces is in the YZ plane.
And that's why you start. It's just
So-
weird having like the y equal
32 squared
on
divided
the
by 9.
inside.
Correct answer is
Just the way that we
6,410
did it,
square root of
like
5
y
over
equals c plus
100.
2. It's usually on like the first one. It's like, what I'm saying is.
Yes, I understand. So let's set it up with the Y surfaces.
Okay.
So if we set it up with Y surfaces, if we set it up like they did, so let's see, if we set it up like they did, and let's do it as a double integral so Taryn doesn't freak out, then we'll do the right surface minus the left surface.
Okay.
So the right surface is this one, so that's y equals z plus 2.
Okay.
So that's going to be z plus 2, that's the right surface.
Minus.
Minus the left surface is going to be this one. So we have to solve that for y. That's this right here.
Right.
So now we've written these as surfaces as opposed to lines. Right? Do you understand the difference?
Yeah.
So here, when we think of them as surfaces, we're thinking of them as extruded out in the x direction. But in this case, we're thinking of just this plane, this region in the YZ plane, because this is the two-dimensional domain over here. So here we're thinking of these as lines. Here we're thinking of them as surfaces.
Okay.
So this is the right surface minus the left surface. And then the domain for right minus left, so if we're doing the y's, the domain should be in what plane?
XZ.
XZ plane. So up here we have the YZ plane, so now we have to look into the XZ plane for the domain.
Okay.
So let's take a look in the XZ plane.
But it's still just an iPad.
This is the domain for
Let's just say
Okay, so in the XZ plane, what do we have? So in the XZ plane, x is going from 0 to 7. So let's, I guess we just go this way. So x is going 0 to 7. And what is z going from?
I can't. Can you go back up a little bit?
Yeah,
Yeah, 0.
that's it.
Oh, yeah, that's what it was.
Just a line. Yeah, so we just get this.
I like that better.
Yeah, me too.
It's great. Okay.
Yeah, it's a little easier.
And then we just do, we can do up or down, we can do y.
So if we do it the way they did it,
DZ.
they did dz dx.
So they did it vertical.
dz dx, they did it vertical. So x is going to go 0 to 7. I guess it doesn't really matter.
0 to 4. Nice.
I
Okay.
still don't know what
But
they're
that's-
putting out there.
That's literally this though, because
Yeah,
you have
exactly.
the 7 and all you've
It's
done is
probably-
subtract.
Yeah,
it.
yeah. Yes, exactly. Yes.
I
It's
feel like they're just
probably
putting the
about
7
it.
out there because a lot of times in these examples they'll want you to put
Out here?
Yeah. I
So
feel like-
let's see what they're putting out there. So
Oh.
what they're going to put out there is this. We're going to go one more step and combine these guys. So we get 3/3 plus 1/3 is 4/3 z. And then the constants, they have 2 plus that. So 6/3 plus 2/3 is 8/3. So here's what they're going to put out
Oh.
there.
I see it.
They're going to pull out 4/3.
Yeah, that's what they did.
That's what they're putting out there.
It's so weird they make us do that.
I know, that's an oddball thing to put out there.
I mean, it's-
It makes you feel like you're supposed
you
to be
just-
using symmetry.
Or you can
That's
put
what it makes
one
you-
and try a same thing inside.
Yeah, like what he did. Put a
Yeah.
1 out there.
Did
But
it accept it with a
Yeah.
1?
Yeah, I
It did,
one.
okay.
I see why though. It's like because I always pull out constants because I
Mhm,
can't have. That'll
Which is a good habit. It's a good habit, because then
So-
you're dealing with less stuff that you could
But
possibly...
sometimes these problems won't let you like pull that constant out. You have to keep it.
Your mass integral and you divide that in, that's just like average value where you're or instead of dividing by volume or area, you're dividing by mass. So I don't need to sort of do a separate problem, find average value, because you're going to be doing a center of mass anyway.
Okay.
So, okay, so in 13.2, the big thing was finding double integrals over a general region, as opposed to a double integral over a rectangle. So
So like with functions on the
with
side?
yes, with functions on. So we've been doing a ton of those already,
And way more complicated.
in way more
ways.
complex situations than this. So the question is, should we do one from 13.2 or should we go to 13.3?
Well, because 13.3 is polar, right?
Yeah, 13.3 is changing it to polar.
Okay.
So totally up to you guys. Do you want to do one from 13.2 or 13.3?
13.3. 13.4.
We'll definitely do one from 13.4. Definitely 13.4.
And 13.5.
And, yeah,
Two. One of each.
Yeah, we can do a few.
Two?
Okay, so in
Spherical or electrical.
13.3, let's do, I don't know, I think I'm going to pull it up on here so that we can more easily copy it.
13.2.
13.2. All right, so I'm going to go to the study plan. Study plan 13.2. You guys are going to cheer for the one that you want to do. All right, first let's figure out the topic. Volume of the solid using polar or using polar to find an area or one of each.
One of each.
Okay.
All right.
All right. All right, we did it. All right, so here, let's do this one. This one looks pretty cool.
Oh yeah, that's dope.
That looks pretty cool.
It looks very rotund.
Super rotund.
Gold, dude.
I'm sorry, I should be in prison for that, but
Better than
in a trapezoidal
better than being in
Trapezoidal
prison.
prison.
Yeah, if you have a choice between a prison and a prison, pick a prison.
wait, I still don't know which one you mean.
Okay, so this says find the volume of the solid below this paraboloid and above the following region. So that paraboloid is opening down, and we want to figure out what the volume is on this region. So we don't know if the paraboloid is going all the way down to the xy plane, or maybe it's going below it. We just have to look and analyze what the limits are, the lateral limits, the side limits. Okay, so this says, let's go ahead and draw the domain here. So it says that we want to, basically it's looking for part of an annulus because we are going r equals 1 to 2. So there's r equals 1. Let's say that's r equals 2. And they're saying, let's go minus pi over 2 to pi over 2. So we're considering the right side of this annulus in here. So that's going to be our domain. This paraboloid that's opening down above it. Let's figure out what the volume is. So the volume is going to be the double integral of upper minus lower. So we don't even have triples here yet, but could we do it with a triple? Sure. And it would be cylindrical coordinates if we were doing it with a triple. We have an upper surface, a lower surface, and then a polar boundary in the xy plane. So that would be cylindrical. So instead of doing 3 integrals, we'll just do 2 integrals of upper minus lower. So the upper surface is the paraboloid. 6 minus x squared minus y squared. Let's switch to polar right away. So 6 minus r squared. Good.
Times r d r theta.
R d theta. Good. So now that is finding the volume beneath that paraboloid. Now we have to decide on what domain region are we finding that volume. So r is going to go 1 to 2. Theta is going to go
0 to pi and double it.
We could do that. We could go 0 to pi over 2 and double it. Right? Let's do that. That's a great idea.
I mean, couldn't we just collapse it in the beginning?
Probably, actually.
So we can just blast this.
Yeah. Okay, so everybody agree with that? Now, does this paraboloid reach the xy plane with that boundary? Well,
Hold on, where are we getting this to again?
the 2 out here.
Yeah.
So instead of going from minus pi over 2 to pi over 2, we went from 0 to pi over 2 and doubled it. So.
Yeah, I didn't see that. Didn't take note of that 0 there.
And does this paraboloid on this boundary, does it touch the xy plane?
No.
Let's see. So if we want to know where this touches the xy plane, we would set z equal to 0. So we would get 6 equals x squared plus y squared. And that is a circle of radius square root 6. So the radius here is root 6, which is somewhere between 2 and 3, and we're only going out to 2. So the paraboloid is not coming all the way down to the xy plane. So we've got this paraboloid coming down more like a silo with a parabolic lid, and then it's coming down. You follow that? All right. So the paraboloid's upside down, but then we don't hit the xy plane. We just stop at r equals 2, so that we've got like a cylindrical wall on the edge of it. Okay. Now we just integrate that. Do we need to do that integral?
Why not?
No. No, that's.
Let's not.
Because it takes time.
So,
could do
can I?
Yeah,
what-
question?
So, I guess, and this is probably a dumb question, but I guess in my brain, like, you've always said volume, you have, like, nothing in the middle. Why?
If a triple integral of nothing is volume. A double integral of top minus bottom, right minus left, back, front minus back.
Oh, okay.
Right.
Okay.
A double integral
okay.
of a surface change or a triple integral of nothing is volume,
Okay.
right?
Just say that 100 more times.
Yeah,
and I'll
I
be
will.
done.
Oh, Jared, if it was a triple integral, it'd just be 6 minus r squared on
Yeah.
the top, and then you just get
Yeah.
to where you are.
Yeah, exactly. You'd have 0 on the bottom, 6 minus r squared on the top. Yep, exactly. And so now to integrate this, like was pointed out, there's no theta, so we could collapse the outside. Pi over 2 times pi is pi. And then we integrate this, we'd have 6r, so we'd get 6r squared over 2, r to the 4th over 4. Plug in 0 and plug in 1 and plug in 2.
How far
Take
can
the
you go in
difference.
your head?
Yeah, exactly. How far can you go? All right, so that is a volume using polar. That's a great example. Let's take a look at the next group. Let's go
Are we
back.
gonna do the area using the polar?
Yep, that's the next group, was area using polar. So,
I feel like that's easier than finding volume.
so double integral in polar coordinates.
Oh, good.
21 pi over 4.
Yeah, we should do one with cardioids
Got
if
it.
you can find one.
21
Cardioids, check.
I know there's one in the 13.
That is a cardio. No, that's
No, that's a
It's a
rose.
rose.
Oh, that one.
Cardioid is a
that
good one. There's a cardioid.
Yeah, let's do that.
Oh, I asked you about this one.
This
Why
is-
does it highlight the outside on the left?
That's a great question. Is that the right answer?
I think it will.
Yes,
The
that is the
region
right answer.
inside both cardioids, that's got to be a typo.
It's like that on all of them.
Yeah, that's,
Okay.
yeah, I don't know why I did that. That's weird.
Yeah, I think what they're using for rendering is a bit
Because
glitchy.
I
Yeah.
asked him.
Must be. Okay, so should we do one like this?
Yes.
I asked him.
I have one that's
Is
a
it
little
gonna
harder,
show? Is
but
one like this gonna show up on the test?
You should be able to do stuff like this. Cardioids are important.
It's very
In
usual.
other words, yes.
Cardioid could be intersected with a cardioid, or a cardioid could be intersected with a circle. Something,
everyone,
one of
this
those.
one's sine cosine.
Okay,
You
so
want to tell
let's
us which?
first. Oh yeah, I'll tell you on the test. The
The day of.
first question is, let's make sure we know how to graph our cardioids. So remember that you have a cardioid whenever the coefficient, these coefficients have to match. The coefficient that's by itself, the constant, has to match the coefficient of sine or cosine. So it's going to be a cardioid if you have something like 5 minus 5 sine of theta. Cardioid. 4 plus 4 cosine theta. Cardioid. So any of these types of scenarios, these are all cardioids.
So
As long as the magnitudes of those two numbers match.
the sign doesn't matter. The
Sign doesn't matter. The sign is going to move the thing around. Maybe it's going to change the dimple area, but it will not. But it will still be a cardioid. All right. So let's go ahead and do this one where we have ones. So the way we graph these polar ones is to start at theta equals 0 and then rotate all the way around to theta equals 2 pi and just plot. With a cardioid, we need 4 points, and that's plenty. So theta equals 0, plug in 0, we get a value of 1. Plug in pi over 2, sine of pi over 2 is 1, so we get a value of 2. So we're up there. We already probably know what it looks like. Plug in pi, sine of pi is 0, so we're 1 unit away from the origin, so we're out there. Plug in 3 pi over 2. Sine of 3 pi over 2 is -1. So this cardioid is going to have that shape. Second cardioid. Now we're going to go with the cosine one. Plug in 0. Cosine of 0 is 1. 1 plus 1 is 2. So for the cosine one, our first point's out here. Up to pi over 2. Cosine pi over 2 is 0. We're going to be 1 unit away from the origin. Plug in pi. Cosine pi is -1. We're right there. 3 pi over 2. We're right there. So this cardioid is going to look like that. Okay. It's asking for the region that's trapped in between the two. And this picture obviously is not great. Let's pull the picture that they have up here because it's really important to see that there's a little tiny tail right there, a little stem.
Mine's
Apple stem.
It does look like an
You
apple.
have the stem.
Maybe more of a spade.
Yeah,
Yeah.
spade.
A leaf.
Yeah, spade.
Oh, it's right
Aspen
there.
leaf
It's
stem.
an apple.
Yeah, aspen leaf.
Okay, so that, we just have to be careful. We've got that little piece right there. All right. And now we want to find the volume, the area.
Or the top of the
The area that's between the two.
Top of what?
So we have a couple of choices. We could start, it makes a lot of sense to start at pi over 4 and use some symmetry. So if you use pi over 4, start at pi over 4, and then rotate counterclockwise
Yeah.
that way.
7 pi over 4.
And here's where we have a question, and we should ask ourselves, we are going to integrate right through that dimple right there. And in this case, it's totally fine. And there's no mathematical justification that I have come up with yet. I've looked and I've tried so many examples. There's sometimes you can integrate through the dimple of a cardioid and it doesn't make any difference, and other times you can't. And so if I was doing this from scratch and I hadn't tried it a bunch of times already, I would say first find this area there and double it, and then come down here and go from pi to, I think you said 7 pi over 4.
5 pi over 4.
5 pi over 4.
Yeah.
5 pi over 4. And get that little stem piece. You know, if I was doing it for the first time in scratch, I would do it both ways and then say, okay, yeah, I can integrate through the dimple. I don't know why it works. Or what, you know, you should always be careful integrating through this. But if you have a cardioid intersecting a cardioid, you can do it. It's not a problem for some reason. It works.
Please help fund
With
the boss too.
every time with
With cardioid intersecting cardioids and these problems, I checked all the ones in here, they all work. So
there's no way.
Yeah.
I mean, there's a way you could, yeah.
I feel like there's a way we could arrange the cardioids so that it didn't work, but I couldn't find one. It worked in all cases. Yeah, it's puzzling. And maybe, yeah, I don't know. It might be the time where it is a problem if you have a cardioid in a circle, and the circle is resting on one of the axes, the circle is offset, it's not at the origin, then you can't, then it didn't work. I can't quite figure out why exactly yet. Okay, so this does work. So we're going to set up our area integral as 2 times the integral from pi over. I need two integrals. Let me set the double up first. Double integral, and the inner integral is going to be our curves. We're basically integrating nothing in here, so it's area. The r is part of the differential, so we're thinking about integrating nothing, integrating 1. And then our inner curve is what? R equals 0. Our outer curve is the blue cardioid, which was the cosine one, so 1 plus cosine theta. So 1 plus cosine theta. And then how about theta?
It starts from pi over 4.
Yeah, pi over 4 to 5 pi over 4, and that works without splitting it apart. Yeah.
Why is your R 0? I can't see it right away.
So let's clear this out just a little bit.
Okay.
So when we're just focused on this region here, correct?
Sure.
So if I draw a polar element, I'm emanating from the origin.
Oh.
So a polar is just like spherical. Often you're starting at r equals 0 for polar because you're emanating from the origin. So the inner curve is r equals 0. It's just the origin. Just like with spherical, a lot of times you're emanating from the origin and you're creating, you're dealing with like a cone. So with spherical, you're thinking about this type of thing often, and you're coming from the origin. So your inner surface is rho equals 0, and your outer surface is rho equals a sphere, or whatever it is. Same with polar. You're emanating from the origin. R equals 0 is that dot, and you're coming out to the outer curve. Yeah. Will?
Yeah, so pretty much, let's say that we didn't know that the dimple thing would work, and you want it. So pretty much what you need to do is split up into two, and or find out you have to figure out where at what angle r would equal to 0.
Yes. So 0, and it'll turn out that's pi. So we go 0 to pi, this top part, and then from pi to 5 pi over 4, the same exact function.
Yeah.
Right. Yeah. And it works fine.
So then, so you went from 0 to 1 plus cosine theta because we were doubling it, but if you weren't doubling it, we would go from 1 plus sine theta to 1 plus cosine theta.
Yeah.
No. Say that again?
If we're not doubling the integral,
Yep.
then our lower limit's not 0. What would our lower limit be?
Our lower limit, we would be going from
It would still be
minus 5 pi over 4 all the way to 5 pi over 4.
Oh, I see. That's because
So
of
it's-
the angle.
Yes, it's because of the angle. So the angle that we're starting at, the pi over 4 is right there,
I get
and
it.
we're rotating, this direction. So if we weren't going to use that symmetry, we would be starting all the way back here at negative 5 pi over 4 and rotating all the way around to positive 5
But
pi
the
over 4.
1 plus sine theta.
That would
we're-
stay, the
we're
1
not-
plus cosine theta would stay the
We're
same.
not using the 1 plus sine theta at all.
No, not at all.
Okay.
Yeah. What we're using it for is to figure out where this angle is.
Okay. Makes sense.
So the red cardioid, the only purpose of it really is to tell us which portion of the blue cardioid we're trying to find the area of.
Okay.
Right. So that right there. And did I say that correctly though? Minus 5 pi. No. We can't go minus 5 pi over 4 to 5. We have to use symmetry here. We have to use symmetry. If we weren't going to use symmetry, we would do this without the 2, plus we would go from minus 5 pi over 4 to pi over 4 with the red one.
Okay.
So if we're not going to use symmetry, we would integrate the blue one from pi over 4 to 5 pi over 4, but then integrate the red one from minus 5 pi over 4 to pi over 4.
So that's when you would use both.
Then we would use both. We'd use the blue one for one integral and the red one for the other integral.
That makes sense.
Sorry about that. I was thinking it would still be the same cardioid, but it's a different cardioid if we start at minus 5 pi over 4.
Okay.
And minus 5 pi over 4 is the red one, right?
Yeah.
Not the blue one.
That makes sense.
Easier to use symmetry though. Hung?
So if we don't have the small part, so we go from pi over 4 to what?
Say that again. If we don't have
The small part.
that little stem,
Yeah.
if we don't have that,
Yeah.
then we go
So
from
when you go from pi over 4 to where?
to pi.
Just pi.
Yeah. So if you look at the blue cardioid, 1 plus cosine of theta, if you want to know where that's going to be equal to 0, that means cosine of theta equals negative 1, so theta is going to be pi. So that's going to be where the blue one touches the origin again. So at pi. All right, let's go to 13.4.
That's a great idea. Because I have to.
Okay.
So 13.4. Triple integrals.
Yeah.
Okay, so in 13.4, we have volumes finding triple integrals. We have change of integration order. Should we do one volume first?
Yes.
Volumes, yes.
Yeah, perfect.
Yeah, let's not do that.
I'm gonna talk to you about like low and high and what they equal and they're just equal and constant.
Let's take a look at this thing. All right, so let's find the volume of this wedge.
This looks like something we did in 13.7. You know, where we changed had to change the region.
Yeah, we have to identify the region that we have to identify surfaces, which ones we want as the inner limits. The inner limits. So triple integral.
This is painful.
So we have to decide front, back, left, right, up, down.
Down.
What do you want to do?
Up, down.
Up, down, definitely. That's the only one that works.
No. Up, down. Is that the only one that works?
No, it's not.
No. Is that the only one that works?
You do left and right.
Oh, yeah, you're right. It is the only one that works.
Wait.
Because it's tilted.
Exactly.
Oh.
Right? It's rotated.
Wait.
Yeah,
Couldn't you
good
go
point.
through that way?
Right? So if we were to treat this as the left and that as the right, but it's tilted, we'd have to do a Jacobian if we were going to do it that way. Do you see that there's not a unique left-right or front-back?
No.
No? No. So do you see that the left surface over here is tilted? Right? It's not parallel to a coordinate plane. The back of this wedge right here, this back, the left side of that wedge, if you look at the base of it, it's tilted in there. It's not parallel to the XY plane. So think about the trough that we did. The trough that we did, the directions that worked were parallel to coordinate planes. We had x equals 0, x equals 7, z equals 0, z equals 4. That back wall, this rectangle right here, that's tilted sideways. It's rotated. If you look in the XY plane, it's rotated with a negative slope on that intersection curve. You agree? Now, if the whole thing was rotated so that this black rectangle is perpendicular to the y-axis, then yeah. Then we could definitely use a different direction. But the only direction we can use relative to its current position is top-bottom. It's the only one that's going to work. Let's take it might be a little clearer if we draw a picture of the domain in the xy plane. So the domain in the xy plane is going to be that square or rectangle we don't know quite yet. Let's look more carefully. So what about the y-intercept and the x-intercept? What are those guys?
12 and 12.
So 12 and 12 in the positive direction and in the negative direction?
Negative 12.
Negative and negative. So we're imagining this
It's kind of like a diamond.
diamond thing.
Kite.
It's a kite. So wow, it's not so good. I think I can do better. Okay, so we're imagining a kite. Oh, I can do better. There we go. There we go. That's much better. That looks so much better.
Revolutionary.
Revolutionary.
I love this class.
Oh my god. Not this one. Okay, so 12 and 12. So now can you see more clearly why we couldn't use the front, back, left, right thingy?
Thingy.
Right, because you'd have to have intersections parallel to the y-axis or the x-axis. Because this is extruded this direction, there's all wonky.
Oh, it's like okay, it's like a pencil almost, like the
Yeah.
the old school pencils.
Yeah,
like,
yeah. With the,
Okay.
it's like a pencil.
Gotcha. I don't know why that makes sense for any reason.
Square
If it works to think of it as a pencil, go for it. Okay, so what is the upper surface?
12 minus y minus x.
Mm-hmm, exactly. 12 minus x minus y. And the lower surface? So those are our two surfaces. So z equals 0. So this is a dz. Then let's go down here. We have to figure out, should we use a vertical or horizontal element? They look equally wretched. So if they're equally wretched, let's draw a vertical element.
Could you do it by 4?
Can we do what?
Can you
We can use
just
symmetry.
do that first quarter?
So so we have to be a little careful because if we are going to use symmetry, we have to be very careful with symmetry here. We could use symmetry if we go from if we somehow chop it through the y equals x line.
Using one.
Oh, whoops.
Oh boy.
If we chopped it through the y equals x line, we could use symmetry. I don't think that's going to help us, though. So let's use a vertical element from there to there. So the x's are constant. Those are on the outside. And those are negative 12 to 12. And then the y's.
Negative y plus 12.
Negative y plus 12, and then,
Minus 12 and plus 12.
let's see, is that right?
I think that was switched.
One should be y.
Y
Minus 12.
minus 12.
This one, yeah, that one right there is y minus 12 down there. Y minus 12. And then what's the upper one?
12 minus y.
12 minus y. Okay, so now is this finding, how much of the volume is this finding?
Wait,
Shouldn't that be in terms of x though?
wait, that's all of it.
Oh yeah, this is,
That's all of it.
yeah, this should be x.
Yeah, y equals.
There you go.
Y equals y.
Yeah, y equals y. Okay, but now originally I said x goes negative 12 to 12. Can x go negative 12 to 12?
No.
Where should x go from?
0 to 12.
0 to 12. And then we have to add, because this is definitely not symmetric. If we look along the y-axis, that is not symmetric. So then we would have to add a second triple with the same, mostly the same stuff, negative 12 to 0. And now, what would our lower curve over here be?
12 minus x.
So the lower one,
Negative x plus 1.
Minus 12 and x.
the y-intercept is negative 12. The slope is negative 1. So I'm thinking negative x minus 12. Over to positive 1 is the slope. 12 is the y-intercept, so x plus 12. So that would be our setup. We won't go through any more of it, but setup's the important part. So that's a tricky one because you can't use symmetry there in any easy way. No easy way. Okay, so another one from 13.5, or sorry, 13.4.
Can we do one where you switch the...
Switch the order of integration.
We gotta do some spherical too.
Okay, switching order of integration. Let's grab that
Yes.
one first.
We
Very
can
much
figure
so.
these ones out.
You have to correct it. You have to separate the axis because the axis
Oh, I like
is
this one.
fucked up. So if you're going left to right, you're actually going along the x-axis, which means that this surface here can have this
Okay,
surface.
rewrite the order of integration.
Yeah, because the back is technically
These-
left and right. Yeah. So it's 'cause it's tilted.
Very important. There's definitely going to be a solid where you have to reverse the order of integration. Okay, so the most important integral here is the inner one, just because this is our surfaces. The inner integral represents the surfaces, and if you don't get the surfaces right, the outer two don't even matter. You've got to get the inner surfaces right, the inner integral surfaces right. Yeah?
So for these kind of problems, we need to draw it, right?
I would recommend drawing it.
If you don't,
If you don't draw it, it's going to be almost, I mean, if you're very, very good at visualizing, you might be able to get the limits. But if you don't draw it, it's very, I find it very difficult to get the limits. All right, so let's figure out what the inner integral is representing. Certainly y equals 0 is just the xz plane. We know that. So we have the xz plane. That's our left surface. So this should be our left surface down here, and this is our right surface up there. So y equals 4x plus 4. That's going to be our right surface. When x is 0, y is 4. When y is 0, what is x? When y is 0, x is
Four.
negative 1. Negative 1. There we have it. There we have it.
0, 4.
There we have it.
Negative 1.
It's got to be an integer. Okay.
We'll know how to math.
Negative 1. All right. So we have that. If we connect those dots, there is no z in that equation. So what do we do with that?
Extruded.
We extrude parallel to the z-axis. So that's going to come up that direction. So we're getting this plane.
Get on planes, man. Why can't it be cars?
Planes are easier to draw.
Amen.
Hold on.
That sounded like a Seinfeld joke.
So this plane continues on through the y-axis this way, and
you know,
so it's a
Oh, I
vertical.
see,
You see
yeah.
it? So it's a vertical plane sitting on the xy plane.
Yeah, I see it. Yeah, so it's
Okay,
like,
so
yeah, a little
now-
weird since we're drawn in that quadrant or octant.
Not octant, exactly. So let's go to the domain over here and let's figure out what's happening. So remember that with a triple integral, these limits here, the dx, dy, the outer two integrals, that represents the domain for the two surfaces that we just talked about. The domain for the two surfaces, the surfaces that are the lower and the right, or the left and the right.
What, isn't our domain dx dz? Not dx dy?
Nope. Oh, I'm sorry. I squared the wrong thing. Thank you. I'm meant to be doing this. Yes. Thank you. Okay, so our domain is in the xz plane. In the xz plane, x is going from -1 to 0. It's not oriented very well. -1 to 0. And y is going from, or excuse me, z is going from 0 to 7. Now that's just a rectangular region. So our rectangular region looks like that. And what direction is the element to begin with? Is it vertical or horizontal?
Horizontal.
So z is coming from this constant interval, so z's constant interval, so they've given it to us as a horizontal element. That's how they've given it to us. And now they want us to reverse it. So let's come over to our picture and see if we can picture what's happening here. So z is going 0 to 7. The domain is in this xz plane back here, and we're going -1 to 0. So okay, so that's in that. Let's use that color, I guess. So right there. So the domain looks kind of like that. Everyone okay with that? And that's going up to 7 on the y-axis, z-axis, the vertical axis.
Yeah, so
having a little trouble figuring out where y equals 0 is.
That red square I just draw, that red rectangle, that's in y equals 0. Right? Y equals 0 is the xz plane.
All right, yeah, no.
So,
So-
you just drew
so
that
this-
onto there?
Yes. So
Okay.
this rectangle here is that rectangle there.
Okay.
Yeah. Not to scale. Not to scale. All right. So now they want us to switch, and we want to use the,
It's so much easier when I was in these GeoGebra.
yeah, it helps to have geometry, to have some sort of graphing package. So Z is on the inside, so now we're using upper and lower surfaces. So what would the lower surface be?
0.
0. Well done. What is the upper surface?
7.
Well done. And now the domain is in the xy plane. So we have to look over here and we have to recreate the xy plane so we can figure out how our limits are going to look. So there's x, there's y. It looks like the x-intercept is -1, the y-intercept is 4. So in the xy plane, that is our domain. That is the domain for z equals 0 and z equals 7. So if you're up here thinking about this, z equals 7 is this surface up here. That's your upper. That's your lower.
Did you just take what you had on the bottom and just
Yep.
draw it on there?
Mhm.
Okay.
So right there, y-intercept is 4, x-intercept is -1. So that triangle is that triangle. Triangular prism. And then based on the order of integration that we want, y is coming last. So y coming last means that we have a horizontal element. So the y's will go 0 to 4.
I broke the law of cosines and I went to triangular prism.
Stop breaking laws of cosines. Those are really important rules.
Can't do the crime, don't. Wait, can't do the time, don't do the crime.
Can't do the time. Don't do the
Got
crime.
me there.
So
All
then
right,
X
so then the x limits are,
0 to that
No.
line.
1
gonna
for
be a
y
function.
minus y over 4 minus 1.
so which limit should be 0?
The top one.
Top. Right, we're going left to right.
Oh.
Right, left to right, so now we need that diagonal line as our left, but we have to write it as an x value. X equals something, so an x value. So let's write that line right there. That is y equals positive slope of 4, x plus 4. Is that right?
You have it right above it too.
Oh yeah, right there. We already had it. We already knew it. We were able to construct it correctly. So we have to write it as an x value though. So x is going to be equal to y minus 4 divided by 4. So we'll write it as 1/4 y minus 1. That's going to go right in there. And then we reverse these. So we did it. Order has been reversed. So both of those, if you integrate, you get the exact same volume, obviously. It would be stupid.
Yeah, we'll be able to go over the problem involving pretty much taking a hemisphere intersecting a offset circle.
Mm-hmm.
Yeah, which one was that?
Mm-hmm.
I don't remember where it was.
I know what you're talking about.
That one was.
That one's tricky. So any questions on this one? So let's talk about the one that Will's alluding to. What if we have, let's look at it as a cross section, just to make sure that we kind of get the general scheme of it. So we've got that, and I believe we're talking about this type of scenario there.
Except in 3 dimensions.
Yes, except it's 3-dimensional. This is a cross section. So let's imagine this as being the xz right there, or the yz, doesn't matter. Maybe it's more intuitive to use that as yz, it doesn't matter, either way. Xz or yz. Okay, so let's imagine this And now the ones that you were dealing with this, were the spheres of the same radius?
Yeah.
They had the same radius? Okay. So let's imagine that this one right here is rho equals 4. So that's a sphere of radius 4, centered at the origin. This one, what would its equation be if it's offset and it has a radius of 4?
4 plus.
Rho equals 4 cosine phi, is that what you said? Let's check. You're going to agree with him if he's right?
4 plus, I think.
So let's figure out, what does 4 cosine phi look like? If we wanted to convert this over to rectangular, let's check. If we multiply both sides by rho, we would have that. This is x squared plus y squared plus z squared. This is 4z. Z is rho cos phi. R is rho sine phi. Everyone okay with that? We have that very, very important triangle that relates. That does not work. Is everybody okay with that, or should I remind you of the triangle that we used to? So we have this right triangle where this was z, this is rho, this is r, that's phi.
Theta's on the bottom.
Theta's on the bottom. Yep. So rho cos phi is z, rho sine phi is r. So then we do a little subtraction, complete the square. So we get that. Is that what we wanted?
Shift it up to.
Does it have a radius? So the center is has a 0, 0, 2, so that would be the center. So the radius of this is 2, but what's the radius of that one? 4.
Doesn't it say 2 squared?
No,
But that's not the radius is always the square root of the right side. So we're very, very close. What do we do?
Double.
So if we make this an 8, let's see if that does it. Bless you. So if we make that an 8, then this is going to be an 8. That's going to be an 8. Divide by 2 and square, we make that a 16, which would make this a 16, which would make this a 4 squared. Now we have a radius of 4, and this would be z minus 4. So that would do it.
So 8. That's weird.
So the radius of the circle is half that coefficient. Half that coefficient.
But wouldn't z minus 4 put our center at the top?
So the center of that one is 0, 0, 4. So this is 4 right there.
Oh, okay.
Right, that's 4. This would also be 4 out to here. I have a radius of 4. Okay. So we've constructed the equation of a sphere of radius 4 that's resting on the xy plane. And now I think the questions in the homework were asking for the volume. Were they asking for the volume of this region?
Yeah.
Volume of that region? So now we have to be really careful here because we cannot do it directly. We have to do some subtraction. So here's why we can't do it directly. When we emanate from the origin and come out, here the inner curve is the origin, the outer curve is this curve, and if we're thinking in terms of surfaces, the inner surface is the origin, the outer surface is this sphere. But as we rotate, we have this point of intersection there. And then we have this element here. So the element here is hitting the blue sphere. The element here is hitting the black sphere. So we can't just do it directly with one triple integral. We would, if we wanted to try to do it directly, we would have to do a triple integral where we go from 0 to the blue plus 0 to the black. So that's why the recommendation would be find the area of the whole sphere and then subtract off this stuff. Because that you can find in one integral. One triple will find the volume of this piece. Omar?
Why could we not just use the bottom problem and the bottom sphere and the top sphere as the bounds?
So are you saying these points right here? Those points?
Yeah, so you have that little black half hemisphere that's facing up.
Yep.
Why can't you use that as the bottom bound and the top blue sphere as
Yep.
the top bound?
So that's because a spherical, or it's easier to conceptualize it with polar. So if we imagine it in polar, it works just fine, right? The outer curve here is blue, but the outer curve here is black. So if
Right.
you're drawing a spherical element straight out from the origin or a radial element for polar, you can do it, but you have to break it into two triples.
Right, but why can't you use that, instead of having 0 as your bound for the radius,
Mm-hmm.
why don't you have that little black area?
Like this?
Yeah,
Draw it vertically, you mean?
kind of. Yeah, just like that.
Well, we're using spherical coordinates here
So
because
it doesn't.
it's not going to translate well to.
Okay.
So what you're basically suggesting is let's do it with cylindrical.
Mhm.
But writing each of these spheres with cylindrical is going to be
More work than it's
Really
worth.
hard.
it's going to be really hard. It's going to be a pitta. Yep. It's going to be a pain in the analysis. So what we would rather do is find the volume of the black sphere and then find the volume of this complementary region and subtract that off. And that will find the volume that's trapped between the two spheres. Okay, so the reason, so let's get these guys out of there. Okay, so we definitely are going to need to know what those green points are. And is it clear that if we emanate from the origin that we do have a consistent inner and outer surface when we rotate? Right, so as we rotate that element left and right, like a windshield wiper, it's always going to have this as the outer surface, always this as the inner surface, all the way to the green dot, all the way to the green dot. Right, so that is a simple single triple integral. So let's do that. So the first, let's find, I guess, the volume of the black sphere. And what's that going to be? 4/3 pi r cubed. So 4/3 pi times the radius cubed. So whatever that is, 256 pi over 3, I think. 64, 4 times 4, 64, right, 128, 256. Okay, so that's the volume of the black sphere. So now we're going to find the volume of the complementary solid, whatever we want to call that. So the what? Yeah.
You said something.
Hemisphere?
Ah.
It's not really a hemisphere though, right?
Oh.
Because it's
like
that
a-
weird crescent moon rotated
Oh, that
around. Like a,
Don't-
what is it?
A helmet.
A helmet. Yeah,
Like a
it's like a
bad
helmet.
helmet.
It's like a helmet. It's a very protective helmet.
Or the
It's a
little
helmet
dude
with
from Mario
nips.
Party. The little dude with Toad.
Yeah, that too.
Yeah, a little like head mushroom.
Yeah, exactly. All right, I'm glad you guys can see it. So the inner surface is rho equals 4. The outer surface is rho equals 8 cosine phi. Because we're in spherical, we have a rho squared sine phi here, and then d rho d phi d theta. And then phi is going to go 0 to what? 0 to whatever. So phi is 0 up here. We have to figure out what the angle of intersection is right there. So we're going to have to come down here and calculate the angle for this rotation. So we need to figure out
pi
that
over 3.
angle.
You think so?
Yeah.
It certainly looks pi over 3-ish.
I think it's there.
To figure it out, we just set the two equal to each other. So we're going to set these two equal to each other.
You're definitely right.
Cosine of phi is going to equal 1/2. So phi is going to be
You're right.
pi over 3.
Yep.
Well done. Well done. 0 to pi over 3. Good grief. 0 to pi over 3. Theta. 0 to 2 pi. So that is the volume of the complementary, whatever we want to call it. We'll call it VC, volume of the complement. What we're looking for.
So I have a question.
Yeah, questions.
So the reason why the limits are from 0 to pi over 3 instead of from like pi over 3 to 4 pi over 3, which is where the other intersection is, right?
Oh.
It's because you're going from the z-axis down.
We're going from the z-axis down, exactly. So it's pi over 3 this direction. So
Yeah.
this angle here would be pi over 6. And then we rotate that all the way around. Phi equals pi over 3 is a cone.
Yeah, and then it gets rotated all the way around by 4.
And it's going to take into consideration that point of intersection on the other side.
Okay,
Yep.
I just wanted to make sure.
Yep, so pi over 3, top down. Do we need to? I don't think we need to, but so whatever we get here when we integrate this, rho cubed over 3, plug that in, integrate with trig sub, not trig sub, u sub, blah, 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 subtract it from the 256 pi over 3, and that would be your answer.
But don't we have to half that? Because it's only up there, it's only, like on your graph, it's
Mhm.
only half empty.
So when we use these limits, we're going
you're doing
from,
that was the black one.
so the black one, that is going to be the whole sphere right there is volume.
Okay. And then you're subtracting off that a little bit.
And then we're going to subtract off this whole, the helmet. We're going to subtract off that helmet piece.
Oh.
So the helmet piece is the volume of this. We're finding, the volume of all of that. That green is not too better to use the highlighter, I guess. So we're finding the volume of this whole piece in here. And then subtracting that off from the volume of the sphere. That's right. All right, next section.
Oh, question.
Question?
Why is it 0 to 2 pi? For
Because your head, to cover your entire head,
Okay.
with the helmet, we've got to go all the way around. Yeah.
You may want to leave a gap in.
For your face?
Yeah, probably gonna
So
have
you
to
can
do
see?
something funky for phi.
Wait, why? Faces.
All right, so that was in section 4. So what do we want to do for section 5? What type of question?
What's section 5 about again?
Section 5 is the
Oh, spherical.
Cylindrical.
Definitely some spherical in the 50s.
all right. So spherical coordinates,
Maybe
triple
in the
integrals.
But you're not going to give us any information like that, are you?
I am not going to draw all of these pictures for you.
No, I just mean like the limits. You're not going to give us
Oh.
the limits.
No, not always.
Okay.
So I've got to give you one or the other. I can give you the picture and then you create the limits, or I can describe it and you can create the limits.
We're not going to have to draw a three-dimensional object.
There's only one in which you really have to draw three-dimensional, and that's where you're interchanging the limits. That's the only
Oh.
one where you have to draw.
Okay, gotcha.
So this is a good one to understand. We could modify it a little bit. Let's see if there's another one where they give us a little less information. What is that? Hello.
There's one where you have like a mound. They don't give you any.
Ooh,
That's
ooh,
what we
ooh.
that's what we just did.
Oh, we just.
So let's look at this. This is a good one to understand. We see it a lot. And the part that's important here that is really easy to get confused on are these limits. Let's just make sure that's clear. Page. Let's grab this half. Page. Okay, so spherical planes and spherical Has everybody got those down? So this right here, 7 secant phi, that is the plane z equals 7. And when you look at that equation, when you look at 7 secant phi, it's not obvious that that's a flat plane, right? When you think of secant, you think of a wiggly curve, a wiggly trig function that's got repeating, these things. So it's not obvious that that's a plane. But mathematically, it should be really obvious. It should be easy for us to conclude that it's a plane because we look at rho equals 7 secant of phi, and what do we do to both sides? No.
Turn it into cosine.
No.
Cosine.
No. Yes! So this turns into rho cosine of phi equals 7. And in spherical, what is rho cosine phi? Z. Z equals 7. Right? Z equals 7. So that shows us mathematically very easily that secant of phi times 7 is really just a plane. It's not intuitive, though. Not intuitive. You don't look at 7 secant phi and say, oh, look at that nice smooth plane.
I don't like that.
Right?
I don't look at rho cosine phi and see a plane either.
Yeah.
Rho cosine phi is not a plane. It's a circle, right?
Rho cosine phi is the z coordinate.
Oh, I'm thinking like the other side. Never mind.
Okay, so that is an important thing. So we see a lot of these things in this section where we have cones capped with a plane or cones capped with a sphere. So either a snow cone type thing where the cap is a sphere or this triangle, cone with just a flat top. All right, so to find the volume of this, we would do the inner surface down here, the outer surface up there. So when you're imagining your spherical element, you're coming from the inner surface, which is the origin, and then you hit the flat top there. All right, so the inner surface is rho equals 0. The outer surface is rho equals this plane. If you had a sphere as that outer surface, like in a snow cone, it would just be rho equals whatever the radius of the sphere is. And now we have to match the domain with the phi and the theta. So to figure out what phi is, what do we do?
Look at the picture.
Yeah, in this case, you look at the picture. So we have, and theta's obvious, right? 0 to 2 pi. We have 3 choices for phi when you have a cone. There's only 3 choices. I am not going to give you a phi that is not a special angle. So you're rotating from here. It's either pi over 6, pi over 4, pi over 3. One or the other. So your cones, you can have r equal, let's see. R equals, what's the cone in spherical? It's z equals, so it's 4, like something like this, right?
4 minus
No,
R.
wait, what am I doing here? Cone. A cone. What's the equation of a cone?
Z equals square root of x squared plus y
Oh,
squared.
yeah. Thank you. I have the wrong letter on the left. It's z equals, so I want to be doing this.
Isn't that
So-
just the upper half?
Yes.
Oh, but that's all you want.
That's all we want, yep. So if we do something like that, that's going to be a cone, right? And let's write this in rectangular. You'd have this, something like that. So what about, here are the choices. So I have that choice, and what is phi for that one?
Definitely pi over 4.
Pi over 4. Pi over 4 is phi for that one. Why? If you erase this, you're going to end up with getting a absolute value function that bisects in the xz plane or in the yz plane. Here are the other 2 choices. You could have 4 minus, you could have 3x squared minus 3y squared. That's one choice. And the last choice is this. You could have a 3 down here and a 3 down here. Those are the only choices. Let's just quickly, I'll do this as fast as I can, graph these 2. So here, if you were to let y be 0, so that we're in the xz plane, we get the square root of that. So we get z squared. I can't graph very fast. D.
Can you guys stay for an extra minute, everybody? Who doesn't have to write?
Yeah. Oh, you know what my problem is right now? I can't graph fast. That's one of my problems. That's one of my problems. When we let y equals 0 here, let me just think about this real quick. Z squared. So we have z squared equal x squared plus z squared. I'm not getting the square root of just x squared though. There shouldn't be a 4 there.
There's what you wrote earlier.
Yeah, what did I write earlier? Yeah, let me take this out here. Let me take this out. This is stupid. This is stupid. This is what it should look like. I wrote my cones down wrong. These are cones. That's a cone. I thought we said 4 minus. This is a cone, right? If you let x be 0, you get z equals square root of y squared, so you get z equals absolute value of y. Or if you let y be 0, you get z equals absolute value of x. I don't know why I had the 4 in there. So these are the 3 choices. That one's pi over 4. Here, if you let the y's be, ooh, let's not do it that way. Here, if you let the y's be 0, then you get z equals the square root of 3 times the absolute value of x. So you're going to get a steeper situation. And if the slope is square root of 3, that means you're at this is pi over 3 or this is pi over 6. So this is going to be a phi equals pi over 6. And down here, if you let y be 0, you get z equals the absolute value of x divided by the square root of 3. That's going to be a less steep cone. That's going to be down here, where phi is going to be 2 pi, excuse me, pi over 3.
How the hell do you not have those switched?
Pi over 3. Say that once again.
How is pi over 6 or pi over 3 not switched? Because pi over 3
Because phi rotates from the z.
Oh, it's rotating from the top.
So
using
phi
the top as
rotates,
normal.
yeah,
Yes.
phi rotates from the up there. Yeah. So those are the only 3 choices: pi over 6, pi over 4, pi over 3. So if I give you that cone, you know it's pi over 4. That one, you project and you see what phi has to equal. Yeah. Yeah. I'm sorry about that 4 in there. I don't know why I was thinking that was a cone with a 4. What is it? What is it if there was the 4 in there? If it's 4 minus x squared minus z squared, that's a sphere. It's an upper hemisphere.
I still can't.
Oh, those upper hemispheres. My upper hemisphere is
I still can't get that.
I need to crack a prism.
When